Next, that's a very important concept is partial discharge measurement. So before that, we should understand what are the detectors which is used in the dielectric loss measurement. For the DC and the low frequency measurement, DC calorimeter and DC amplifier with micrometers are used. In the case of power frequency measurement, vibration calorimeter are also used. So in the case of audio frequency range, wideband or tuned null detectors are also used with a sensitivity of better than 10 microvolts. So other than this, cathode ray oscilloscope also used as a detectors. If too high a sensitivity is not required. So the selection of the detectors depends on the type of the bridge and the measurement and the sensitivity which is required in the particular application. So then coming to this partial discharge measurement. So earlier in the case of testing of the insulator and other equipments, so based on its resistance measurement, dissipation factor, tan delta, and the breakdown test. So generally it is observed that the tan delta, that's a dissipation factor, was depend on um, voltage, and hence it is become a criteria for monitoring of high voltage insulation. So in further investigation, it is found that the weak points in the insulation like voids, cracks, and other imperfections will lead to that. It is found that weak points in the insulation like void, cracks, and other imperfection will lead to the internal or intermittent discharges in the insulation. So these are small but not revealed in the capacitance measurement, but were revealed as a power losses component in contributing for increase in the dissipation factor. So in the modern terminology, so these are designated as, we can call it as partial discharges. So this is the definition which is asked in the examination. So which in course of the time reduces the strength of the insulation will lead to that the total or the partial failure, or there is a possibility of the breakdown of the insulation may takes places. So this is the one of the insulating devices with a wide and a simplified electrical equivalent which we can see here. So if the partial discharges can be located inside an equipment like in the case of power cables or the transformer, it is gives an valuable information for the engineer of the insulation about the reasons of the there is a greater stress and there is an imperfection in the fabrications. So based on this information, designs can be considerably improved. So by considering that electrical insulation with the imperfections like voids, or this will lead to that, but the voids, or we can call it as any imperfections which is a present, will lead to that partial discharges which can be represented by the equivalent circuit you can see here. This is CA, the void act like an spark gap. CB is nothing but the capacitance of the remaining insulation, and this is a remaining capacitance of the total object. Okay, CC, CA void, CB rest of the things, and this is total value. So when the voltage across the capacitor which is raised, a critical value, if it is reaches across the CA, the wire, and a discharge occurs through the capacitor, that is nothing but that is it becomes a short circuited. So this is represented by closer switch. Okay, this is a CA across the wire, CB is remaining there. This is the total value of the capacitance. So which you can see here, this is the waveform where we can see here minimum and goes on maximum, and the minimum across there is a y. So generally this is what is the value of the CA, which is very small compared to the CB and the CC. So and there is a charge which was present in the capacitor CA will flows through that the CB and the CC. So gives rise to an voltage pulse across the CC value. So the measurement of the pulse across the capacitor will give us the amount of discharge quality. So but this measurement is difficult in practice, and an apparent charge method across the detecting impedance is usually made. So there are the two different methods for measuring, that is nothing but straight discharge method. Straight this is nothing but detection using straight detector, and we have balanced detection method. So this is the one of the circuit diagram for the straight discharge detection method. The circuit diagram which you can see here shown at this point. So the high voltage transformer, this is the high voltage transformer which is shown here. It is free from the internal discharges. There is an resonant filter which is used to prevent the pulses which are starting from the capacitance of the winding, okay, capacitance of the winding and bushing of the transformer. So there is a CX, this is nothing but the test object, okay. This is the CC is nothing but the coupling capacitor. So ZM is nothing but detection impedance, and the signal which is developed across the ZM is passed through is considered as band pass filter, and there is an amplifier, okay, band pass filter C3, and there is an amplifier which you can see here, band pass filter and amplifier, and there is an counted by the pulse counter. There is a multi-channel analyzer unit. The partial discharge, the detector which is connected across the measuring impedance ZM, so which is shown in here. The signal which is measured across this impedance which is read by the detector, the signal voltage which is developed across the ZM, which is depending upon the circuit parameters, that is nothing but the CX and the coupling condenser, and also the internal circuitry of the instrument. So the measurement or the detector is generally calibrated by injecting a pulse having a charge of known magnitude in the detection system. So for this purpose there is a square wave generator, and there is an calibrating capacitor which is CK are usually used. So the magnitude of this charge injected, that's Q is equal to CK into VK. So where VK is nothing but a magnitude of the voltage pulse. The rise time of the pulse is generally is of the 0.1 microsecond, and there is a pulse width of around at 10 to 20 microsecond. So with the suitable attenuator, so the output voltage pulse which can be varies from minimum output of value of around 10 microvolt to maximum value of 100 volt, which is in steps. So the value of the CK, so usually used, which is lies between 1000 and 2500 picofarad. So if this calibrating pulse is directly injected at the high voltage terminal of the test object, okay, at this point, the magnitude of the calibration pulse will be multiplied by CK into VK. and the pulse which is injected across the measuring impedance, then the calibrating pulse magnitude should be the multiplied by the Cx plus Cc divided by Cc. So there is another method of calibrating which is used to measure the secondary standard, which is consisting of a point hemisphere electrode system of the specimen dimensions. So this is method is more accurate and easily reproducible with an over voltage of 10 to 20% is applied above the discharge insufficient voltage. So the arrangement will give us discharges which are used for the calibration purposes. However, having some limitation, to overcome this limitation, we are going with balanced detector method. However, what are the errors which is introduced by the outside, it cannot be nullified by using this circuit. So far we are going with a balanced detector. This is a partial discharge pattern. So here discharge pattern which is displayed on the CRO screen of a discharge detector with elliptical display which you can see here. So in that figure A, this is elliptical sweep display, and in the case of the B and C, there is a corona discharge. In the case of this is a point and the plane, and in the case of negative discharge pulses in the wires if there is an insulation, which you can see here, and this is the discharge in the wires bound on one side with insulation and other side which is considered as the conductors. So here the discharges usually start near the peak of the test voltage, but it is start spread towards the zero value as the test voltage which is goes on increasing beyond the insufficient level. The number and the magnitude of the discharge on both the positive and the negative cycles are approximately the same. Okay, so a typical discharge pattern from wire bounded on one side by an insulation and other side by a conductor, which is shown here. Okay, at this the figure C. So this pattern discharge in common, which is common in the case of the uh, cross-linked polyethylene cables. So when there is a discharge which is made of large number of the pulses of the small magnitude on the positive cycle, and there is a much smaller number of a large magnitude pulses on the negative cycle. So this is a very difficult to see to that there is a small differentiation among these things. So in the narrow band detector scheme, with the impedance LC circuit tuned for 100 kilohertz. So this is the one of the way which you can see here. So in the case of point of plane, okay, so this is start sweeping towards, there is a pulse formations across. This is start moving from negative from zero, start from zero to the negative values. So if there is a wire which you can see is depending upon the value of the negative and the positive polarity. Okay, so it is depending upon what kind of the supply which you are going to give it. In the case of the cross-linked polyethylene cables, so basically you are going to study these things in the relay and the high voltage labs. Next concept is balance detection method. So in the case of the straight detector method, the external disturbances are not fully rejected. The insulator which is used to block the noise sources may not be effective. So hence the sharing bridge which is employed for the tan data measurement sometimes which is used. So in this method the test is not grounded. So there is a modification of the sharing bits. Detector is the differential discharge detector, which is given by Kruger. So these both schemes are given in the figure. Next one. So the bridges are tuned at a balance at the frequency of 50 Hz. So there is a filter which is used across the detector terminal, which is to block the 50 Hz component of the frequency which is present. So signals in the range from 5 Hz to 50 kHz, which is allows to pass through the filter and which is amplified. So there is an CRO which gives the display of the pulse pattern. So any external interferences from the outside which is balanced out, only internally generated pulse are detected. So this is the circuit diagram where you can see the balanced retrievers in the sharing bits. So any external interferences from the outside which is balanced out by this bridge, and only the test specimen which is CX generated by this, it is pulse generated or detected. So whereas in case of this modified one, so there is another test sample. This is CX and having the internal resistance R value. So generally we'll call it as dummy sample, which is used in the place of the standard capacitors. So the capacitance CX, the capacitance and the tan delta of the dummy samples are made approximately equal. So, but need not be an equal, because it have the limitation that if the two discharges, that's nothing but CX1 and the CX2, if there is a two discharge occurs in both the samples simultaneously, so there is a possibility of the cancel out may takes places. So there is a possibility is very rare to takes place cancellation of these things. So the main advantage of this second method is, so its accuracy, its capacity for the better rejections of the external noise, and which is used for the wide frequency band with better resolution of the individual pulses. Last concept is discharge detection in power cables. So the power cables which having the grade length may be considered to be specimen with distributed capacitance rather than the lumped capacitance. So this is the future is true for the winding of the transformers and the rotating machines which having the high voltage ratings. So in such cases, the location of the discharge, this is done using the traveling wave techniques. So this is discussed in the case of how we tested um, the location of the fault in the case of the power cables. So the breakdown or the discharge in a cavity, considering that the location is F, will causes there is a charge accumulation at the fault point. We are considering it is F. So this will create, there are the two traveling waves which travels in opposite direction. Okay, one is traveling toward the transformer end, another to the low voltage potential divider which is connected to the CRO or the measuring instruments. So by considering that the voltage wave is given by, so VI is equal to the impedance into the current and divided by 2. Okay, by considering this there is an CC, that's nothing but coupling condenser is neglected in this comparison, and the detection impedance, that is nothing but ZD. The voltage signal across this, the detection impedance will become, so VD is equal to the impedance ZD divided by ZT plus Z naught into the Z naught into IT. That's nothing but we know what is the voltage division formula. Okay, if considering that, what will happen? ZD is equal to, okay, so ZD is equal to Z naught. What will happens at this point? VD is equal to Z naught into I of t divided by 2. So okay, at this point, so if there is a partial discharges which is located exactly in the case of the middle, okay, so here the traveling wave moving, which is moving to the left, which is reflected without any the polarity changes at the open end, and then what will then this will arise at the detection impedance having the ZD, so which is separated from the direct pulse by the time which is equal to the cable transient time tau. Okay, so this is the tau which we are considering, that the time constant. So if the site is at any other points, then what will happens? There is a time difference at this point. Okay, if it is not exactly at the middle, then there is a time difference between the original and there is a reflected. It may be values varies from 0 to 2 tau. So usually what will happens? The supply transformer end, this point end is not strictly an open circuit, because it having the some shunt capacitance because of the high voltage terminal uh, of the transformer. So therefore, what will happens? The traveling wave which is reflected from the transformer end, which having the surge impedance, because we are considering the impedance of the transformer and its terminations. So to avoid these things, there is a reflection and the inductor which is going to be inserted. This is the portion where I'm pointing towards, which is inserted at the transformer end. So by knowing this, there is an transit time of the cable, the T, and there is an actual time. So based on these differences, the fault position can be located. So here the identification of the fault position is a quite a challenging task for the being an engineer, because a lot of the research and a lot of the work is going on to identify this kind of the position. I think you might be knowing that in the year of 2017, so there was an the blackout. Some portion of the Bangalore, it's not blackout. Some portion of the Bangalore could not able to get the power. Because of this, there was a problem with an underground cable. So I think it took around 1.5 months to rectify that the location. So this is the quite challenging task of being an engineer, to find out and to location, finding that position, and to once it is located, and we have to do a separation. So this is the quite challenging task. So this completes this model, the entire model. Thank you everyone.